Imagine standing at the edge of an infinite ocean, holding a single cup of water in your hands, believing that you understand the depths, the currents, the creatures, and the secrets of the entire sea because you have examined that tiny cup. Now imagine discovering that the ocean stretches not just beyond the horizon, but beyond your wildest imagination. That the cup you hold represents less than a fraction of a fraction of a fraction of what exists, and that everything you thought you knew about the water, about the life within it, about the very nature of oceans themselves, might be completely wrong. This is not a metaphor or a thought experiment. This is the exact situation humanity finds itself in right now, at this very moment in our cosmic history, because scientists have just revealed something that should shake us to our core, something that fundamentally changes our understanding of existence itself. They have shown us, through careful observation, rigorous mathematics, and humbling honesty, that everything we have ever seen, everything we have ever studied, every galaxy we have photographed, every star we have cataloged, every planet we have discovered, every particle we have detected, all of it combined represents less than 5% of what actually exists in the universe. The other 95% is invisible to us, unreachable by our telescopes, undetectable by our instruments, and yet it controls everything, shapes everything, and determines the fate of everything. Tonight, we will journey together through this revelation, exploring what scientists have discovered about the vast unseen universe, understanding why we have been so blind for so long, and contemplating what it means for humanity that we have seen so little while assuming we understood so much. Wherever you are right now, whether you are settling into the comfort of darkness, letting your body relax after a long day, or simply allowing your mind to drift into wonder, I invite you to join me on this exploration of cosmic humility, of the boundaries of human knowledge, and of the staggering reality that we are far more ignorant than we ever dared to admit. Before we begin this journey into the unknown, if you find value in these explorations, a subscription helps keep these cosmic conversations alive. And now, let us step together into the humbling truth of how little we have truly seen, the illusion of knowledge. For thousands of years, humanity has looked up at the night sky and believed we were seeing the universe. Ancient astronomers counted the stars they could observe with their naked eyes, numbering perhaps a few thousand visible points of light, and they created elaborate systems to explain the heavens, drawing constellations, predicting eclipses, and building monuments aligned with celestial events. They believed they were witnessing the totality of creation, that the visible stars represented all that existed beyond Earth. As telescopes improved, we saw more, discovering that our Milky Way galaxy contained not thousands, but hundreds of billions of stars, that beyond our galaxy lay countless other galaxies, each containing billions or trillions of stars, and that the universe stretched far beyond anything our ancestors had imagined. We felt proud of this expanding knowledge, confident that our instruments were revealing the true nature of reality. The 20th century brought revolutionary discoveries in physics, revealing the quantum realm at the smallest scales and the relativistic universe at the largest scales. We developed theories that seemed to explain everything from the birth of the universe in the Big Bang to the eventual fate of every star and planet. We built massive telescopes, launched satellites into space, constructed particle accelerators underground, and created sophisticated computer models that simulated the evolution of cosmic structure. Each new discovery reinforced our belief that we were approaching a complete understanding of the cosmos, that we were filling in the final gaps in our knowledge, that soon we would have a unified theory explaining all physical phenomena. But beneath this confident veneer of expanding knowledge, something troubling was emerging. Astronomers measuring the motions of galaxies found that stars were orbiting far too quickly to be held by the gravity of visible matter alone. Physicists studying the expansion of the universe discovered that space was accelerating outward, pushed by an unknown force that should not exist according to our theories. Cosmologists calculating the amount of matter produced in the Big Bang found that the numbers did not match observations, that something was missing, something vast and invisible. These anomalies, these cracks in our understanding, were not minor discrepancies that could be explained away with small adjustments. They were fundamental contradictions pointing towards something shocking: the universe we can see, the matter we can detect, the energy we can measure. All of it represents only a tiny fraction of what actually exists. The rest, the overwhelming majority, is composed of things we have never directly observed, things that do not emit light or interact with ordinary matter in ways we can easily detect. This invisible universe shapes everything we see, determines how galaxies form and evolve, controls the expansion of space itself, and yet remains profoundly mysterious despite decades of intensive study. The discovery of dark matter. The first hints that something was deeply wrong with our picture of the universe came in the 1930s, when a Swiss astronomer named Fritz Zwicky was studying a group of galaxies called the Coma Cluster. Zwicky measured how fast individual galaxies within the cluster were moving, using the Doppler shift of their light to calculate their velocities. When he added up all the mass he could see in stars and gas, he found something impossible. The galaxies were moving so fast that they should have escaped the cluster long ago, flying apart like sparks from a fire. The gravity from the visible matter was nowhere near strong enough to hold them together. Zwicky concluded that there must be a huge amount of invisible matter in the cluster, matter that provided the extra gravity needed to keep the galaxies bound together. He called this invisible substance dark matter, but his discovery was largely ignored for decades because it seemed too radical, too strange, too contradictory to accepted physics. The evidence accumulated slowly, building through the work of astronomers like Vera Rubin, who in the 1970s studied the rotation curves of spiral galaxies. A rotation curve shows how fast stars and gas are orbiting at different distances from a galaxy's center. According to Newton's laws of gravity, stars farther from the center should orbit more slowly, just as the outer planets in our solar system orbit more slowly than the inner planets. But Rubin found that in galaxy after galaxy, the rotation speed stayed roughly constant or even increased at large distances from the center. This flat rotation curve meant that there had to be far more mass in the galaxy than could be accounted for by visible stars and gas. The only explanation was the presence of enormous halos of dark matter extending far beyond the visible edges of galaxies, halos containing 5 to 10 times more mass than all the stars combined. At first, astronomers hoped that dark matter might simply be ordinary matter that did not emit much light, perhaps brown dwarfs, dead stars, black holes, or massive planets. These objects, collectively called MACOs for massive compact halo objects, could exist in large numbers without being easily visible. But careful searches using gravitational microlensing, where a foreground object bends the light from a background star, showed that MACOs were far too rare to account for all the dark matter. Whatever dark matter was, it had to be something fundamentally different from ordinary atoms, something that interacted with regular matter only through gravity, something that passed through planets and stars and even us without ever touching anything. Physicists proposed that dark matter might consist of exotic particles created in the Big Bang, particles that had never been detected in laboratories but which were predicted by extensions of the standard model of particle physics. Names like WIMPs, which stood for weakly interacting massive particles, and axions, which were hypothetical particles with very small mass, became common in scientific literature. Experiments were built deep underground to search for these particles, using tanks of liquid xenon or other materials that might register a rare interaction with a passing dark matter particle. But despite decades of searching with increasingly sensitive detectors, no dark matter particle has ever been definitively detected. The revelation of dark energy. Just as astronomers were coming to terms with the reality that most of the matter in the universe is invisible, an even more shocking discovery emerged in the late 1990s. Two teams of scientists, working independently, were studying distant supernovae to measure how the expansion of the universe was slowing down. Everyone expected that the expansion would be decelerating because gravity from all the matter in the universe should be pulling everything back together, acting as a brake on the outward motion initiated by the Big Bang. The teams measured distances to dozens of supernovae in galaxies billions of light-years away, using the fact that certain types of supernovae always have the same intrinsic brightness, making them perfect standard candles for measuring cosmic distances. When they compared these distances to the red shifts of the galaxies, which indicated how fast they were receding due to cosmic expansion, they found something that seemed impossible. The distant supernovae were fainter than expected, meaning they were farther away than they should be if the expansion were slowing down at the predicted rate. The only way to make sense of the data was if the expansion of the universe was not slowing down at all, but was instead speeding up, accelerating over time. This discovery was so unexpected, so contradictory to everything that was understood about gravity and cosmology, that both teams checked and rechecked their data countless times, looking for errors, but the conclusion remained inescapable. Space itself was expanding faster and faster, driven by some mysterious force that pushed galaxies apart, a force that became stronger as the universe grew larger. This force was given the name dark energy, and its existence implied that our understanding of physics was profoundly incomplete. Dark energy behaves unlike anything we have ever encountered. Whereas matter, both ordinary and dark, clumps together under gravity, dark energy is spread uniformly throughout space, and its density does not dilute as the universe expands. Imagine a room where you spread perfume, and instead of the scent dispersing and weakening as it fills the space, it maintains the same strength everywhere. And as the room gets bigger, more perfume appears to keep the concentration constant. This is how dark energy behaves, permeating every cubic meter of space with a constant energy density that exerts a repulsive gravitational effect, pushing space apart. The nature of dark energy remains one of the deepest mysteries in physics. One possibility is that it represents the energy of empty space itself, what quantum field theory calls vacuum energy. According to quantum mechanics, even empty space is not truly empty, but is filled with virtual particles constantly appearing and disappearing, and these fluctuations contribute energy to the vacuum. The problem is that when physicists calculate how much vacuum energy there should be, the answer comes out absurdly large, about 10 to the power of 120 times larger than the observed dark energy density. This enormous discrepancy, called the cosmological constant problem, is one of the worst predictions in the history of physics. Other theories propose that dark energy is a new type of field, sometimes called quintessence, that changes over time and varies from place to place, or that our theory of gravity itself needs modification on cosmological scales. Despite decades of study, dark energy remains deeply mysterious, and its discovery revealed that not only do we not understand most of the matter in the universe, we also do not understand most of the energy. The cosmic census. When scientists added up everything we know about the universe, combining observations of galaxy motions, measurements of cosmic expansion, analysis of the cosmic microwave background radiation, and calculations of how much matter was produced in the Big Bang, they arrived at a cosmic inventory that is humbling in its implications. Ordinary matter, the stuff that makes up everything we can see and touch, the atoms that form stars, planets, gas clouds, and our own bodies, accounts for approximately 4.9% of the total energy and mass in the universe. Dark matter, the invisible substance that dominates the gravitational landscape, makes up about 26.8%. Dark energy, the mysterious force accelerating the expansion of space, comprises about 68.3%. These numbers mean that everything humanity has ever observed directly, every star we have photographed, every galaxy we have catalogued, every planet we have studied, represents less than 5% of what actually exists. We are like observers standing in a dark room, able to see only the tiny fraction of objects that happen to be illuminated by a flashlight, while the vast majority of the room's contents remain invisible in the shadows. This realization is profoundly different from simply discovering new objects that we had not noticed before. This is not like finding a new species of animal or a new planet in our solar system. This is discovering that the fundamental composition of reality is almost entirely unknown to us, that the building blocks of the universe are things we have never seen and cannot directly detect. It is as if we had been studying chemistry for centuries, understanding elements and molecules and chemical reactions, only to discover that atoms, the things we thought were the fundamental units of matter, actually make up less than 5% of what exists, and that 95% of reality consists of entirely different substances that follow different rules and cannot be studied with traditional chemistry. The implications are staggering. Every theory we have constructed about how the universe works is based almost entirely on observations of the 5% that is visible. When we talk about the Big Bang, about the formation of galaxies, about the evolution of stars, about the physics of black holes, we are describing processes that are dominated by the invisible 95%, by dark matter that provides the gravitational scaffolding for structure formation, and by dark energy that determines the ultimate fate of the cosmos. Our theories may be approximately correct, but they are built on an incomplete foundation, like trying to understand a forest by studying only the moss on the trees, while remaining blind to the trees themselves, and to the soil, the water, the animals, and the air that make the ecosystem function. The observable universe. Even within the small fraction of the universe that consists of ordinary matter, we have seen only a tiny portion. The universe is vast, beyond human comprehension, and light from distant regions has not had time to reach us since the Big Bang occurred 13.8 billion years ago. This creates an observational horizon, a boundary beyond which we cannot see, because light from those distant regions is still traveling toward us and will not arrive for billions of years. The observable universe, the region from which light has had time to reach Earth, is enormous, with a radius of about 46 billion light-years. This distance is larger than you might expect from a universe that is only 13.8 billion years old, because space itself has been expanding while the light was traveling, stretching the distance between us and the sources of that light. Within this observable sphere, there are an estimated 2 trillion galaxies, each containing hundreds of billions or even trillions of stars, leading to a total stellar population of approximately 10 to the 24th power stars, a number so large it is written as 1 followed by 24 zeros. Despite this staggering abundance, we have studied only a minuscule fraction in any detail. Most galaxies are so distant and faint that they appear as tiny smudges in even the most powerful telescopes, and we know almost nothing about them beyond their approximate distance and brightness. Of the 2 trillion galaxies in the observable universe, we have obtained detailed observations for perhaps a few million, a tiny fraction of 1%. Most stars have never been individually observed, most planets have never been detected, and most of the detailed structure of the cosmos remains unexplored. Even within our own Milky Way galaxy, we have catalogued only a small percentage of the 100 billion or more stars. The Gaia space mission, which is creating the most detailed map of our galaxy ever made, has measured the positions and motions of about 1 billion stars. An impressive achievement, but still only about 1% of the total. For the vast majority of stars in our galaxy, we do not know their precise locations, their ages, their compositions, or whether they have planets. Looking beyond the observable universe into regions from which light has not yet reached us, we face an even more profound limitation. The universe may be infinite, stretching forever in all directions, or it may be finite but so large that we can never see most of it. If the universe is infinite, then the observable universe is an infinitely small fraction of what exists, literally 0%. Even if the universe is finite, most cosmological models suggest it is far larger than the observable region, perhaps hundreds or thousands of times larger, meaning we can see less than a fraction of a percent of the total volume. In these distant regions beyond our horizon, there are galaxies we will never observe, stars whose light will never reach Earth, and perhaps even entirely different physical conditions if the properties of space vary from region to region. The cosmic horizon is not a physical barrier, but an informational one, a limit imposed by the finite age of the universe and the finite speed of light, and it ensures that most of reality will forever remain beyond our reach, no matter how long we observe or how advanced our technology becomes. The limits of detection. Even within the observable universe, within the small fraction of reality composed of ordinary matter, there are vast domains that remain invisible to our instruments. Telescopes detect light, but most objects in the universe either do not emit light at all or emit light too faint to detect at great distances. Cold molecular clouds, vast regions of gas and dust where stars form, are dark at visible wavelengths and can be studied only through the faint infrared radiation they emit or the radio waves emitted by molecules like carbon monoxide. Rogue planets, worlds that have been ejected from their solar systems and drift alone through the darkness of interstellar space, are nearly impossible to detect unless they happen to pass in front of a background star, producing a brief gravitational lensing event. Black holes, regions of space where gravity is so strong that not even light can escape, are by definition invisible, detectable only when they interact with nearby matter, pulling in gas that heats up and emits radiation before crossing the event horizon. Even ordinary stars can be hidden if they are surrounded by thick dust, or if they are simply too far away for their light to be distinguished from the background glow of countless other distant stars. Astronomers estimate that we have directly observed perhaps 1% or less of the ordinary matter in the universe, leaving 99% unseen, hidden in faint objects, cold gas, diffuse plasma, and other forms that do not emit detectable radiation. Beyond the limits of electromagnetic observation, there are entirely different types of signals that we are only beginning to detect. Gravitational waves, ripples in space-time caused by the acceleration of massive objects, were predicted by Einstein over a century ago, but were not directly detected until 2015, when the LIGO experiment observed the collision of two black holes. Since then, dozens of gravitational wave events have been detected, opening a new window on the universe and revealing phenomena that are invisible to traditional telescopes. Neutrinos, ghostly particles that rarely interact with matter, stream through the universe in vast numbers, produced in nuclear reactions, in stars, in supernovae, in black hole accretion disks, and in the Big Bang itself. Detecting neutrinos requires enormous underground detectors filled with water or ice, and even then, only a tiny fraction of the neutrinos passing through Earth can be captured. Cosmic rays, high-energy particles that rain down on Earth from space, provide clues about violent processes in the universe, but their sources are often difficult to identify because magnetic fields deflect their paths as they travel through space. Each of these types of signals represents a different way of observing the universe, revealing phenomena that are invisible in ordinary light. And as we develop new detection methods, we discover that the universe is far richer and more complex than we ever imagined, with entire populations of objects and events that were completely unknown because we were not looking for them in the right ways. The invisible architecture. One of the most important revelations about how little we have seen is that the visible matter in the universe, the galaxies and stars we can observe, is not distributed randomly, but follows an intricate pattern determined by invisible dark matter. Computer simulations that model the evolution of cosmic structure show that dark matter forms a vast cosmic web, with dense filaments connecting massive nodes where galaxy clusters form, and enormous voids in between where few galaxies exist. This cosmic web spans the entire observable universe, creating structure on scales of hundreds of millions of light-years. The visible galaxies that we can see in telescopes are like lights strung along the invisible filaments of the dark matter web, revealing only the brightest parts of a vast underlying structure that remains hidden. Astronomers have spent decades mapping the positions of millions of galaxies to trace out the cosmic web, but these maps show only the luminous matter, leaving the dark matter structure largely invisible. Techniques like gravitational lensing, where the path of light from distant galaxies is bent by the gravity of foreground dark matter, allow scientists to create rough maps of the dark matter distribution, but these maps are far less detailed than maps of visible galaxies. The result is that we have a blurry, incomplete picture of the universe's architecture, like trying to understand the structure of a city by looking only at the streetlights while remaining blind to the buildings, roads, and infrastructure that make the city function. The cosmic web also extends down to smaller scales, with dark matter halos surrounding individual galaxies and subhalos within those halos. Every galaxy, including our Milky Way, is embedded in a dark matter halo that extends far beyond the visible disk of stars, containing perhaps 10 times more mass than all the stars combined. These halos are not smooth, but are filled with smaller clumps and streams of dark matter, the remnants of smaller halos that were torn apart by tidal forces as they merged with the main halo. Detecting these small-scale structures is extremely difficult because they contain little or no visible matter, but their presence can be inferred from the motions of stars and gas, from gaps in stellar streams, and from subtle distortions in gravitational lensing patterns. Understanding the detailed structure of dark matter halos is crucial for understanding how galaxies form and evolve, how stars are born, and how planets like Earth came to exist. Yet most of this structure remains unseen, known only through indirect evidence and theoretical models. The hidden history. The universe has a history stretching back 13.8 billion years, but most of that history is hidden from direct observation. The cosmic microwave background radiation, the faint glow that fills the sky at microwave wavelengths, is the oldest light we can see, emitted when the universe was only 380,000 years old and the first atoms were forming. Before that moment, the universe was opaque, filled with a hot plasma that scattered light, making it impossible to see farther back in time using electromagnetic radiation. This cosmic curtain hides the first 380,000 years of the universe's history from our direct view, a period that includes crucial events like the formation of the first atomic nuclei, the creation of the first electrons and protons, and the moment of the Big Bang itself. To study this early period, scientists must rely on indirect evidence, such as the abundances of light elements like hydrogen, helium, and lithium, which were formed in the first few minutes after the Big Bang, and on theoretical models that extrapolate backward from the cosmic microwave background. The hope is that gravitational waves and neutrinos, which can travel freely through the opaque early universe, might someday provide a window into this hidden era. But so far, our sensitivity to primordial gravitational waves and Big Bang neutrinos is not sufficient to detect them. After the cosmic microwave background era, the universe entered a period called the Dark Ages, lasting several 100 million years, during which no stars had yet formed, and the universe was filled with cold, dark hydrogen gas. The first stars eventually formed, igniting nuclear fusion and beginning to emit light, but these first stars were very different from the stars we see today. They were massive, short-lived, and composed almost entirely of hydrogen and helium, without the heavier elements that later stars would contain. These first stars, called population 3 stars, have never been directly observed because they existed so long ago and at such great distances that their light is too faint to detect with current telescopes. Their existence is inferred from theoretical models and from the presence of heavier elements in later generations of stars, elements that could only have been created in the nuclear furnaces of earlier stars. The James Webb Space Telescope, with its ability to observe in the infrared and peer through cosmic dust, may eventually detect the faint afterglow of these first stars, but for now they remain part of the hidden history of the cosmos. Beyond individual objects, entire epochs of cosmic history remain poorly understood because we have so few direct observations. The era when the first galaxies formed, when supermassive black holes grew at the centers of galaxies, when the universe transitioned from a smooth distribution of gas to the structured web of galaxies we see today. All of these periods are known mostly through scattered observations of rare, distant objects and through computer simulations that attempt to recreate the processes involved. Each new generation of telescopes reveals more about these hidden eras, but vast gaps remain, and much of the universe's history will likely never be fully reconstructed because the evidence has been lost to time, obscured by distance, or simply never produced detectable signals. The quantum veil. At the smallest scales, the universe is governed by quantum mechanics, a theory that describes the behavior of particles and energy at atomic and subatomic levels. Quantum mechanics is profoundly strange, allowing particles to exist in multiple states simultaneously, to be connected across vast distances through entanglement, and to be fundamentally uncertain in their properties. One of the most disturbing aspects of quantum mechanics is the uncertainty principle, which states that certain pairs of properties, like position and momentum, cannot be precisely known at the same time. The more accurately you measure a particle's position, the less accurately you can know its momentum, and vice versa. This is not a limitation of measurement technology, but a fundamental property of nature, a statement that reality itself is inherently fuzzy at small scales. The uncertainty principle means that there is a veil beyond which we cannot see, a limit to how much information we can extract from the universe. At scales smaller than the Planck length, about 10 to the negative 35 meters, quantum fluctuations become so large that the very concepts of space and time break down. We cannot observe anything smaller than this scale, not because our instruments are inadequate, but because the universe itself does not have a well-defined structure at these scales. The notion of an event happening at a specific point in space and time becomes meaningless, replaced by a foaming, probabilistic quantum spacetime that defies classical description. Theoretical physicists speculate about what lies beneath the quantum veil, proposing ideas like string theory, which suggests that the fundamental constituents of reality are not point-like particles but tiny vibrating strings of energy, or loop quantum gravity, which suggests that space itself is made up of discrete loops at the Planck scale. These theories attempt to reconcile quantum mechanics with general relativity, Einstein's theory of gravity, which breaks down at small scales and high energies. But these theories are largely untested and may be untestable because the energy scales required to probe the Planck realm are so enormous that no conceivable experiment could reach them. The most powerful particle accelerator on Earth, the Large Hadron Collider, reaches energies of about 10 trillion electron volts, but to probe the Planck scale would require energies about 10 to the 16th power times greater, equivalent to the entire mass energy of a mountain concentrated into a single particle. This means that the quantum veil may be permanent, that we may never be able to directly observe the fundamental structure of reality at the smallest scales, and that our understanding will always be limited by the inherent uncertainty built into the fabric of existence. The information paradox. Black holes present another profound limit on what we can observe and understand about the universe. When matter falls into a black hole, crossing the event horizon, all information about that matter, its composition, its history, its quantum state, appears to be lost forever. The event horizon is a one-way boundary. Anything that crosses it can never escape or send signals back to the outside universe. This creates an information paradox because quantum mechanics states that information cannot be destroyed. If you know the complete quantum state of a system at one time, you can, in principle, calculate its state at any other time, past or future. But if information falls into a black hole and disappears, this principle is violated, creating a fundamental conflict between quantum mechanics and general relativity. Physicists have debated this paradox for decades, with proposals ranging from the idea that information is somehow encoded on the event horizon, accessible to external observers, to the suggestion that black holes eventually evaporate through Hawking radiation, a quantum process that causes them to slowly lose mass and emit particles, and that the information is gradually released in these particles. However, the calculations suggest that the Hawking radiation is thermal, meaning it is random and carries no information about what fell into the black hole, leaving the paradox unresolved. Some physicists propose that the interior of a black hole is not what general relativity predicts, that instead of a singularity at the center where density becomes infinite and space-time curvature diverges, there might be a firewall at the event horizon that destroys anything that tries to cross, or a fuzzball of quantum strings that somehow preserves information. Others suggest that the very concept of an interior may be an illusion, that from the perspective of an external observer, nothing ever truly crosses the event horizon, but instead is smeared across the surface in a holographic encoding. Regardless of which resolution is correct, the existence of black holes means that parts of the universe are permanently hidden from us. Any matter or light that has fallen into a black hole is beyond our ability to observe or recover, and any information it carried is either lost or encoded in ways we cannot access. Given that supermassive black holes exist at the centers of most galaxies, and that countless smaller black holes are scattered throughout the universe, enormous amounts of matter and information have been swallowed over cosmic history, hidden forever behind event horizons, reducing the fraction of the universe we can study and understand. The multiverse question. Some of the most speculative ideas in modern physics suggest that the universe we observe, even including the unobservable regions beyond our cosmic horizon, may be just one bubble in a vast multiverse containing countless other universes, each with potentially different physical laws, different values of fundamental constants, and different histories. The concept of a multiverse arises from several different theoretical frameworks, none of which have been confirmed, but all of which are taken seriously by leading physicists. Cosmic inflation, the theory that the early universe underwent a brief period of exponential expansion, predicts that inflation does not end everywhere at once, but instead stops in some regions while continuing in others. Each region where inflation stops becomes a separate bubble universe, with its own Big Bang and its own subsequent evolution. These bubble universes are causally disconnected from each other, meaning that no signal can travel from one to another, and they exist in a larger multiverse that is eternally inflating, constantly producing new bubbles. If this picture is correct, then everything we have ever observed is confined to a single bubble, and there are infinitely many other bubbles, other universes, beyond our reach. String theory, which attempts to unify quantum mechanics and general relativity, predicts the existence of extra-spatial dimensions beyond the three we experience, dimensions that are curled up so tightly that we cannot perceive them. The way these extra dimensions are shaped determines the physical laws and constants in our universe, and string theory allows for an enormous number of possible shapes, leading to perhaps 10 to the power of 500 different possible universes, each with different properties. This landscape of possibilities is so vast that it is sometimes called the string theory landscape, and some physicists argue that all of these possible universes might actually exist somewhere in the multiverse. The many worlds interpretation of quantum mechanics suggests that every time a quantum measurement is made, the universe splits into multiple branches, one for each possible outcome. In this view, every time a particle's position is measured, or a radioactive atom decays, or any quantum event occurs, the universe bifurcates, creating parallel worlds where each possibility is realized. If this interpretation is correct, there are not just a few other universes, but an unfathomably large number of parallel worlds, one for every possible outcome of every quantum event that has ever occurred, and we experience only one branch of this enormous branching tree of realities. The multiverse idea is controversial because it may be inherently untestable. If other universes are beyond our cosmic horizon, causally disconnected from us, then we can never observe them directly or receive signals from them, and the multiverse remains a theoretical speculation rather than a scientific hypothesis that can be confirmed or refuted through experiment. Some physicists argue that if a theory predicts unobservable entities, it is not truly scientific, while others counter that the multiverse is a natural consequence of well-established theories like inflation and quantum mechanics, and that we should accept its existence even if we cannot directly observe it. Regardless of the ultimate status of the multiverse idea, it highlights a profound truth about the limits of observation. If there are regions of reality that are forever beyond our reach, not because of technological limitations, but because of the fundamental structure of space-time and causality, then we must accept that the fraction of existence we have seen and can ever see may be infinitesimally small, and that most of reality will remain forever hidden. The measurement problem. Even when we focus on the small fraction of the universe that we can observe, consisting of ordinary matter within the observable universe, there are fundamental limits to how accurately we can measure and understand what we see. Every measurement has uncertainty, arising from both practical limitations of instruments and from fundamental quantum effects. When astronomers measure the distance to a galaxy, they use techniques like observing Cepheid variable stars, whose brightness varies in a predictable way related to their intrinsic luminosity, or Type Ia supernovae, which have a consistent peak brightness. But these methods have uncertainties, typically a few percent, which compound when measuring very distant objects. When we say a galaxy is 10 billion light-years away, that distance has an error bar, a range of possible values, and for the most distant objects these error bars can be quite large. Similarly, measurements of galaxy masses, based on the motions of stars and gas within them, have uncertainties, because we cannot observe every star or gas cloud, and because the contribution of dark matter, which dominates the mass, must be inferred rather than directly measured. Cosmological parameters, like the Hubble constant, which describes the expansion rate of the universe, have been measured by different teams using different methods, and the results do not always agree, leading to what is called the Hubble tension, a discrepancy that suggests either measurement errors or new physics. The composition of the universe, the percentages of ordinary matter, and dark energy are known to within a few percent, but these small uncertainties translate into enormous uncertainties about the actual amounts of these components when multiplied by the vast volume of the observable universe. Beyond measurement precision, there are systematic errors that can bias results in ways that are difficult to detect. If the instruments are not perfectly calibrated, if the assumptions underlying the analysis are wrong, if there are unknown effects that have not been accounted for, then the measurements can be systematically off, giving a false picture of reality. Throughout the history of science, there have been examples of measurements that were later found to be wrong, of phenomena that were thought to be real but turned out to be artifacts, and of entire theories that were abandoned when better data became available. This history teaches humility, reminding us that our current understanding, no matter how confident we are, may be revised or overturned by future observations. The fraction of the universe we have measured is even smaller than the fraction we have observed, and the accuracy of those measurements is limited by both technological constraints and fundamental physical principles, ensuring that our knowledge will always be incomplete and provisional. The frontier of technology. The progress of astronomy and cosmology over the past few centuries has been driven largely by improvements in technology, from the invention of the telescope in the 17th century to the development of digital cameras, space telescopes, gravitational wave detectors, and massive computer simulations in recent decades. Each new instrument has revealed previously unseen aspects of the universe, expanding the fraction of reality that is accessible to observation. The Hubble Space Telescope, launched in 1990, revolutionized astronomy by providing incredibly sharp images from above Earth's atmosphere, revealing distant galaxies, nebulae, and other objects with unprecedented clarity. Hubble has observed more than 40,000 celestial objects over its 3 decades of operation, contributing to thousands of scientific papers and transforming our understanding of the cosmos. The James Webb Space Telescope, launched in December 2021, is designed to observe in the infrared, seeing through dust clouds and detecting the faint light from the earliest galaxies formed after the Big Bang. Webb's images have already revealed galaxies that existed when the universe was only a few 100 million years old, pushing back the frontier of the observable universe. Ground-based telescopes have also grown enormously, with mirror diameters reaching 10 meters or more, and with adaptive optics systems that correct for atmospheric turbulence, allowing ground-based telescopes to achieve resolution comparable to space telescopes. The next generation of extremely large telescopes, with mirrors 30 or even 40 meters across, will be able to detect even fainter objects and study them in greater detail. Radio telescopes have mapped the sky at wavelengths invisible to the human eye, revealing phenomena like pulsars, quasars, and the cosmic microwave background. The Event Horizon Telescope, a global network of radio telescopes working together, produced the first image of a black hole's event horizon in 2019, showing the shadow of the supermassive black hole at the center of the galaxy M87. Gravitational wave detectors like LIGO and Virgo have opened an entirely new way of observing the universe, detecting ripples in spacetime from colliding black holes and neutron stars, events that are invisible in light. Neutrino detectors like IceCube, buried in the Antarctic ice, capture rare interactions of neutrinos with water molecules, revealing high-energy processes in distant astrophysical sources. Despite these technological advances, the frontier of observation remains far beyond what we have explored. The universe is so vast, so old, and so filled with faint and distant objects that even our most powerful instruments can see only a small fraction of what exists. Future technologies, some already planned and some still in the realm of speculation, may push the frontier further. Space-based gravitational wave detectors like LISA, scheduled for launch in the 2030s, will detect lower-frequency gravitational waves from different types of sources. Next-generation neutrino detectors will increase the number of events captured, providing better statistics and revealing fainter sources. Advanced computer simulations running on ever more powerful supercomputers will model the universe in greater detail, predicting phenomena that can then be searched for with observations. Yet even with all these advances, there will remain vast domains of the universe that are inaccessible, not because of technological limits, but because of fundamental physical barriers like the cosmic horizon, the quantum veil, and the opacity of space to certain types of radiation. The hidden dimensions. One of the most speculative but intriguing ideas in modern physics is that the universe may have more than the three spatial dimensions we experience. String theory, one of the leading candidates for a theory of quantum gravity, requires the existence of extra dimensions, typically 6 or 7 beyond the familiar 3, for its mathematics to be consistent. These extra dimensions are thought to be compactified, curled up into tiny shapes so small that we cannot perceive them directly. Imagine an ant walking along a tightrope stretched across a canyon. From a distance, the tightrope looks like a one-dimensional line, but to the ant walking on it, the tightrope has thickness, a second dimension that allows the ant to walk around its circumference. If the thickness of the tightrope is very small compared to its length, an observer far away would see only the one-dimensional line, remaining unaware of the hidden second dimension. In the same way, the extra dimensions required by string theory could be so small, curled up on scales of the Planck length, or slightly larger, that we experience only the 3 large spatial dimensions, remaining oblivious to the hidden dimensions that exist at every point in space. The shape of these extra dimensions determines the physical laws and constants in our universe, including the masses of particles, the strengths of forces, and even the number of particle types that exist. Different shapes, or compactifications, of the extra dimensions lead to different effective physical laws in the 3-dimensional universe we observe. String theory allows for an enormous number of possible compactifications, perhaps 10 to the power of 500 or more, leading to the string landscape mentioned earlier, a vast space of possible universes with different properties. If extra dimensions exist, they could potentially be detected through their effects on gravity at short distances, or through the production of exotic particles in high-energy collisions. Some versions of string theory predict that gravity might become stronger at very short distances, deviating from the inverse square law that holds at longer distances because gravity can propagate through the extra dimensions, while other forces are confined to our 3-dimensional brain, a term used in string theory to describe the 3-dimensional surface in higher dimensional space where we live. Experiments at particle accelerators have searched for such deviations, but have found none, placing limits on the size and properties of any extra dimensions. Another possibility is that extra dimensions could affect the behavior of dark matter or dark energy, potentially explaining these mysterious components as manifestations of physics in higher dimensional space. Some models propose that dark matter consists of particles that can move through the extra dimensions, making them difficult to detect in our 3-dimensional slice of reality. Despite these speculative ideas, there is currently no direct evidence for extra dimensions, and they remain a theoretical construct, part of the vast, unseen landscape of possible realities that lie beyond our current ability to observe or test. If extra dimensions do exist, they represent yet another way in which the universe we perceive is only a small slice of a much larger and more complex reality, with entire dimensions of space hidden from our senses and instruments. The cosmic microwave background. The cosmic microwave background radiation is one of the most important sources of information about the early universe, and it highlights both what we can learn from observations and the limits of that knowledge. The CMB is the thermal radiation left over from the Big Bang, emitted when the universe was only 380,000 years old, and photons decoupled from matter, beginning their journey through space. This radiation has been traveling toward us for more than 13 billion years, and it fills the entire sky, arriving from all directions with almost uniform intensity. The CMB was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who were testing a sensitive radio antenna and detected a persistent background noise that could not be eliminated. They eventually realized that the noise was coming from space itself, from the faint glow of the early universe, and their discovery provided strong confirmation of the Big Bang theory. Subsequent observations of the CMB, using satellites like COBE, WMAP, and Planck, have mapped the temperature of the radiation across the sky with extraordinary precision, revealing tiny fluctuations, variations of about 1 part in 100,000, that represent the seeds of all cosmic structure. These fluctuations are the imprints of quantum fluctuations in the early universe, stretched to cosmic scales by inflation, and they evolved under the influence of gravity to become the galaxies, clusters, and voids we see today. By analyzing the pattern of fluctuations in the CMB, cosmologists can determine fundamental parameters of the universe, such as its age, its composition, its geometry, and the rate of expansion. The CMB tells us that the universe is flat, meaning it has zero overall curvature, that it is composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy, and that it began in a hot, dense state about 13.8 billion years ago. This is an astonishing amount of information to extract from a faint glow in the sky, and it represents one of the great triumphs of modern cosmology. However, the CMB also reveals the limits of observation. The fluctuations we see in the CMB represent the state of the universe at the moment of photon decoupling, but they do not tell us what happened before that moment. The first 380,000 years of cosmic history are hidden behind the opaque plasma that filled the early universe, and we cannot see through that curtain using light. The CMB also averages over vast regions of space, smoothing out small-scale details, so while it tells us about the overall properties of the universe, it does not reveal the fate of individual regions or the detailed structure of the cosmic web. Furthermore, the CMB is a snapshot from a single moment in time, frozen at the instant of decoupling, and while it provides crucial information about the early universe, it does not directly show us how structures evolved afterward. We must use other observations of galaxies at different distances and times to reconstruct the history of cosmic evolution, and there are large gaps in that reconstruction. The CMB is also subject to foreground contamination, emissions from our own galaxy, and from intervening dust and gas that can obscure the faint primordial signal. Separating the CMB from these foregrounds requires careful analysis and introduces uncertainties. Despite these limitations, the CMB is one of the most powerful tools we have for studying the universe, but it also reminds us that even our best observations reveal only a partial picture, and that much of the universe's history and structure remains hidden. The paradox of precision. One of the strange ironies of modern cosmology is that while we can measure certain properties of the universe with extraordinary precision, we remain profoundly ignorant about the nature of most of its contents. We can determine the age of the universe to within a few tens of millions of years, a precision of better than 1%, even though the universe is nearly 14 billion years old. We can measure the Hubble constant, the expansion rate, to within a few percent. We can calculate the density of dark matter to a few significant figures, yet we have no idea what dark matter is, what it is made of, or how it interacts with anything other than through gravity. We can describe the behavior of dark energy, how it affects the expansion of space, but we cannot explain where it comes from or why its density has the value it does. This paradox of precise measurements describing unknown phenomena highlights a fundamental gap in our understanding. It is as if we could measure the exact temperature of a substance to many decimal places, but had no idea whether the substance was ice, water, steam, or something else entirely. We can describe how dark matter and dark energy behave. We can quantify their effects. We can incorporate them into our models, but we cannot explain them, and we cannot predict them from first principles. This situation is deeply unsatisfying to physicists, who seek not just to describe phenomena, but to understand their origins and their connections to other aspects of nature. The standard model of particle physics, which describes the behavior of all known particles and 3 of the 4 fundamental forces, is extraordinarily successful at predicting experimental results, but it does not include dark matter or dark energy, and it cannot explain why the universe has the matter content it does. Extensions of the standard model, such as supersymmetry, propose new particles that could be dark matter candidates, but despite decades of searching, none of these particles have been detected. The cosmological constant, which could explain dark energy as a property of empty space, has a measured value that is absurdly small compared to theoretical predictions, creating the worst fine-tuning problem in physics. Some physicists have suggested that we live in a very special universe where the constants have the values they do simply because if they were different, we would not exist to observe them, a line of reasoning called the anthropic principle. Others argue that the constants are not fine-tuned, but are the result of some underlying mechanism we have not yet discovered. The fact that we can measure these mysterious components so precisely while remaining ignorant of their nature suggests that the universe is far more complex than our current theories capture, and that future discoveries may reveal entirely new layers of reality that we have not yet imagined. The problem of complexity. The universe is not only vast but also astonishingly complex, with structures and phenomena spanning an enormous range of scales, from subatomic particles to galaxy superclusters, and with intricate interactions between different scales. Understanding this complexity is a monumental challenge, and much of it remains beyond our ability to observe or model. At the smallest scales, quantum field theory describes how particles interact through the exchange of force-carrying bosons, with calculations involving Feynman diagrams that sum over countless possible interaction paths. At slightly larger scales, atomic and molecular physics describe how atoms combine to form molecules, how chemical bonds form and break, and how matter acquires its properties. At even larger scales, condensed matter physics describes how vast numbers of atoms interact to produce phenomena like superconductivity, magnetism, and phase transitions, behaviors that emerge from collective effects and cannot be understood by studying individual atoms. Moving to larger scales, biology describes how complex molecules organize themselves into living cells, how cells form tissues and organisms, and how life evolves over time. Astrophysics describes how gas clouds collapse to form stars, how stars evolve and die, how planetary systems form, and how galaxies evolve. Cosmology describes the evolution of the universe as a whole, the formation of large-scale structure, and the ultimate fate of all matter and energy. Each of these domains has its own methods, its own characteristic scales of length and time, and its own sets of phenomena that are important at that scale but negligible at others. Connecting these scales, understanding how phenomena at one level emerge from interactions at smaller scales, is one of the central challenges of science. Emergence is the term used to describe how complex behaviors arise from simple rules. The flocking of birds, the flow of traffic, the patterns of sand dunes, the structure of galaxies, all are examples of emergent phenomena where the collective behavior of many simple components creates patterns and structures that are not evident from studying the components individually. Much of the complexity in the universe is emergent, arising from interactions among countless particles, stars, galaxies, or other entities, and this complexity is often impossible to predict or fully understand from first principles. Computer simulations can model some emergent phenomena, evolving systems forward in time according to known physical laws, but these simulations are limited by computational power and by the accuracy of the physical models used. A simulation of galaxy formation, for example, must include gravity, gas dynamics, star formation, supernova feedback, black hole growth, and many other processes, each with its own set of equations and parameters. Small changes in the parameters or in the numerical methods can lead to significantly different outcomes, and there is no way to know for certain whether the simulation accurately represents reality. The complexity of the universe means that even if we could observe everything, we might not be able to understand it all, because the interactions and emergent phenomena are too intricate for human minds or even supercomputers to fully grasp. This cognitive and computational limit is another way in which the universe remains largely unseen, not because we lack observations, but because we lack the capacity to make sense of the observations we have. The missing baryons. Within the small fraction of the universe composed of ordinary matter, there is yet another mystery: the missing baryons problem. Baryons are particles made of three quarks, primarily protons and neutrons, which make up atoms and all ordinary matter. Calculations based on Big Bang nucleosynthesis, the process that created the first atomic nuclei in the early universe, predict how many baryons should exist, and this prediction is confirmed by observations of the cosmic microwave background. However, when astronomers add up all the baryons they can observe in stars, gas clouds, and galaxies, they find only about half of what should be there. The other half, roughly half of all the ordinary matter in the universe, is missing, or more accurately, it is hidden in forms that are difficult to detect. Recent observations have begun to solve this mystery, revealing that many of the missing baryons are located in the warm, hot intergalactic medium, a diffuse gas with temperatures of 1,000,000 degrees or more that fills the space between galaxies. This gas is so hot that it emits mostly X-rays, which are difficult to detect because they are absorbed by our own galaxy and by the Earth's atmosphere. The gas is also very tenuous, with densities far lower than the best laboratory vacuums, making it nearly invisible even when it does emit detectable radiation. Observations using X-ray telescopes in space have detected some of this gas, and observations of distant quasars have found absorption lines that indicate the presence of diffuse gas along the line of sight. These observations confirm that the warm, hot intergalactic medium contains a significant fraction of the missing baryons, though the exact amount is still uncertain. Even with this discovery, the fact that half of the ordinary matter in the universe is in such a diffuse and difficult to detect state highlights how much of reality remains hidden even when we restrict our attention to the familiar matter that we thought we understood. Ordinary matter, the stuff we can in principle see and touch, the atoms that make up planets and stars and our own bodies, is distributed in such a way that most of it is invisible, scattered through vast intergalactic spaces in forms that are exceedingly difficult to observe. This realization adds to the humbling picture of how little we have seen, showing that even the small fraction of the universe that is made of normal atoms is mostly hidden from direct observation. The mystery of magnetic fields. Magnetic fields permeate the universe, threading through galaxies, filling interstellar space, and extending across galaxy clusters, yet the origin and evolution of these cosmic magnetic fields remain poorly understood. On Earth, magnetic fields are generated by the motion of conductive fluids, like the molten iron in the planet's core, through a process called the dynamo effect. Similar dynamo processes are thought to operate in stars, generating the magnetic fields that produce sunspots and solar flares. But the details of stellar dynamos are complex and not fully understood. On larger scales, galaxies have magnetic fields that align roughly with the spiral arms and that play important roles in many astrophysical processes. Magnetic fields affect the motion of charged particles, channeling cosmic rays and influencing star formation by providing support against gravitational collapse in gas clouds. They also mediate energy transfer in supernovae and active galactic nuclei, where material is ejected at high speeds along magnetic field lines. Despite their importance, cosmic magnetic fields are difficult to observe directly. They can be detected through their effects on light, such as Faraday rotation, where the plane of polarization of light is rotated as it passes through a magnetized medium, or through synchrotron emission, the radiation produced by charged particles spiraling around magnetic field lines. Radio telescopes can map the distribution of synchrotron emission, revealing the structure of magnetic fields in galaxies and galaxy clusters. But these observations are limited to regions where there are energetic particles, and they do not show the field in empty space, or in regions where the field is weak. The origin of cosmic magnetic fields is also a mystery. In the early universe, shortly after the Big Bang, there were no magnetic fields, or at most only tiny seed fields produced by quantum fluctuations. How these seed fields grew to the large-scale, organized fields we see in galaxies today is not fully understood. Dynamo processes can amplify weak fields, but they require some initial field to work with, and the source of that initial field is unclear. One possibility is that fields were generated during structure formation as gas clouds collapsed and rotated, stretching and twisting any small fields that were present. Another possibility is that fields were created by the motion of charged particles in the early universe, or by exotic processes involving phase transitions or the decay of massive particles. Without a clear understanding of how cosmic magnetic fields originated and evolved, we are missing a crucial piece of the puzzle of galaxy formation and cosmic structure. Magnetic fields represent yet another component of the universe that is largely hidden, detectable only through indirect effects and difficult to map comprehensively, leaving much of the magnetic landscape of the cosmos unseen and unexplored. The unseen neutrinos. Neutrinos are among the most abundant particles in the universe, yet they are extraordinarily difficult to detect, making them a prime example of how much of reality is hidden from our instruments. Neutrinos are produced in vast quantities by nuclear reactions in stars, by supernovae, by cosmic ray interactions in the atmosphere, and by radioactive decays on Earth, and billions of them pass through your body every second without interacting with a single atom. This ghostly nature arises because neutrinos interact only through the weak nuclear force and gravity, both of which are extremely feeble at the level of individual particles. The probability that a neutrino will interact with matter is so small that a neutrino could pass through a light year of solid lead and still have only about a 50% chance of interacting. Detecting neutrinos requires enormous detectors and enormous patience. IceCube, a neutrino observatory at the South Pole, uses a cubic kilometer of Antarctic ice as a detector, with thousands of sensors embedded in the ice to watch for the faint flashes of light produced when a neutrino interacts with a water molecule. Even with this massive detector, IceCube detects only a few dozen high-energy neutrinos per year from astrophysical sources. a tiny fraction of the neutrinos passing through the detector. Other neutrino observatories, like Super Kamiokande in Japan, use large tanks of ultra-pure water, while detectors like Antares and KM3NET use the Mediterranean Sea as a detection medium. Despite decades of operation, neutrino astronomy is still in its infancy, having detected neutrinos from only a handful of sources. The Sun, a nearby supernova that exploded in 1987, cosmic ray interactions in the atmosphere, and a few distant blazars. The cosmic neutrino background, the relic neutrinos from the Big Bang, predicted to fill the universe with a density of about 300 neutrinos per cubic centimeter, has never been directly detected because these neutrinos have extremely low energies, making them even more difficult to interact with than the higher energy neutrinos from other sources. The difficulty of detecting neutrinos means that the universe is filled with signals that we are almost completely blind to. Every supernova releases most of its energy in neutrinos, far more than in light, but we can detect only a tiny fraction of those neutrinos if the supernova is close enough. Every active galactic nucleus, every merging neutron star, every other violent astrophysical event produces neutrinos, and these particles carry information about conditions inside the sources, information that is inaccessible in other ways because light cannot escape from the dense cores. The neutrino universe is largely unseen, a hidden layer of reality that we are only beginning to glimpse, and that will require much larger and more sensitive detectors to explore fully. The cosmic rays enigma. Cosmic rays are high-energy particles, mostly protons, that constantly bombard Earth from space, arriving from all directions and with a vast range of energies. The most energetic cosmic rays carry as much energy as a well-thrown baseball, concentrated into a single subatomic particle, an astonishing amount of energy that requires extreme astrophysical processes to produce. Despite more than a century of study since their discovery in 1912, the sources of cosmic rays, especially the highest energy ones, remain mysterious. Lower energy cosmic rays are thought to be accelerated in supernova remnants, where shock waves from the exploding star accelerate particles to near light speed through a process called diffusive shock acceleration. However, the highest energy cosmic rays, those with energies above 10 to the 18 or 10 to the 19 electron volts, cannot be produced by supernovae and must come from even more powerful sources. Candidates include active galactic nuclei, where supermassive black holes accelerate particles in powerful jets, gamma-ray bursts, the most violent explosions in the universe, and colliding galaxies, where shock waves on enormous scales might accelerate particles. The challenge in identifying the sources is that cosmic rays are electrically charged, and as they travel through space, magnetic fields deflect their paths, scrambling their directions so that by the time they reach Earth, they appear to come from random directions rather than pointing back to their sources. The highest energy cosmic rays, which travel more nearly in straight lines because their enormous momentum makes them less susceptible to deflection, are exceedingly rare. With only a few detected per square kilometer per century, this makes it difficult to gather enough data to identify patterns or correlations with known astrophysical objects. The Pierre Olguet Observatory in Argentina, which covers an area of 3,000 square kilometers and uses a combination of ground detectors and fluorescence telescopes to detect cosmic ray air showers, has been operating for more than a decade and has detected thousands of high-energy cosmic rays, but the sources remain elusive. Beyond the mystery of their origins, cosmic rays are important because they interact with gas and dust in space, producing secondary particles like pions, which decay into gamma rays and neutrinos. Studying cosmic rays thus provides information about conditions in distant regions of the universe, but the difficulty of detecting them and identifying their sources means that much of this information remains inaccessible. The cosmic ray sky, a map showing where these particles originate, is mostly blank, with only a few tentative associations and no confirmed sources for the highest energy particles. This represents yet another way in which the universe is largely unseen, with energetic processes occurring throughout the cosmos that we can detect only through the faint traces left by a tiny fraction of the particles they produce. The gravitational wave horizon. Gravitational waves have opened a new window on the universe, allowing us to observe phenomena that are invisible in light. But like other forms of observation, gravitational wave astronomy has its limits, and vast domains of the gravitational wave universe remain unexplored. LIGO and Virgo, the current generation of gravitational wave detectors, are sensitive to waves with frequencies of a few tens to a few thousand hertz, which correspond to the final moments of merging black holes and neutron stars with masses comparable to or larger than the Sunday. These detectors have made remarkable discoveries, confirming the existence of gravitational waves, revealing a population of black holes with masses that were unexpected, and detecting the collision of neutron stars, along with electromagnetic counterparts that confirmed many predictions about how heavy elements are formed. However, gravitational waves span a much broader range of frequencies, and most of this spectrum is inaccessible to current detectors. At lower frequencies, from 10 to the -4 Hz to 1 Hz, gravitational waves are produced by supermassive black holes with masses of millions or billions of suns, which merge when galaxies collide, a process that takes millions of years, but which produces powerful gravitational waves during the final stages. These low-frequency waves cannot be detected on Earth because seismic noise and other disturbances overwhelm the signal, but they can be detected from space. The Laser Interferometer Space Antenna, or LISA, planned for launch in the 2030s, will consist of 3 spacecraft in a triangular formation separated by millions of kilometers, using laser beams to measure tiny changes in distance caused by passing gravitational waves. LISA will observe a different population of sources, including supermassive black hole mergers, the inspiral of stellar mass objects into supermassive black holes, and possibly signals from the early universe. At even lower frequencies, from 10 to the -9 Hz to 10 to the -6 Hz, gravitational waves can be detected using pulsar timing arrays, networks of radio telescopes that monitor the precise timing of signals from pulsars, ultra-stable natural clocks. Gravitational waves passing through the space between Earth and a pulsar will cause tiny changes in the arrival times of pulsar signals, and by correlating the timing of many pulsars, astronomers can detect these waves. Pulsar timing arrays are currently searching for a gravitational wave background, the cumulative signal from all the supermassive black hole mergers throughout cosmic history, and preliminary results suggest that this background may have been detected, though confirmation requires more data. At the highest frequencies, above thousands of hertz, gravitational waves could be produced by exotic sources like cosmic strings, hypothetical defects in space-time left over from the early universe, or by phase transitions in the first moments after the Big Bang. These high-frequency waves are extremely difficult to detect and require entirely different detector designs, some of which have been proposed but not yet built. The fact that we can currently detect only a narrow band of gravitational wave frequencies means that most of the gravitational wave universe remains unseen, with countless mergers, inspirals, and other events occurring throughout the cosmos that produce signals we cannot yet observe. As new detectors come online and as existing detectors are upgraded, the gravitational wave horizon will expand, revealing more of this hidden universe. But even then, there will be limits, and some sources will remain forever beyond our reach. The undetected dimensions of space. Beyond the three spatial dimensions we experience, there may be additional dimensions that are hidden from us, not only in the sense of being curled up at small scales, as in string theory, but also in the sense that we might be confined to a lower dimensional subspace within a higher dimensional universe. The idea of brains, short for membranes, is central to some versions of string theory. In these models, the particles and forces we experience are confined to a three-dimensional brain embedded in a higher dimensional space called the bulk. Gravity, unlike other forces, can propagate through the bulk, which is why it appears weaker than the other forces at the scales we observe. If this picture is correct, then there is an entire higher dimensional reality existing parallel to our three-dimensional world, and we are like creatures living on a sheet of paper, unaware of the three-dimensional space in which the paper floats. This idea has profound implications for cosmology and for the limits of observation. If there are other brains in the bulk, they could be nearby in the extra dimensions, but completely invisible to us because we cannot send or receive signals through the bulk except via gravity. These other brains could contain entire universes with their own particles, forces, and structures, existing just a tiny distance away in an extra dimension, but forever inaccessible to our telescopes and experiments. Some models propose that dark matter might reside on another brain or in the bulk, interacting with our brain only through gravity, which would explain why it is so difficult to detect. Other models suggest that the Big Bang was not the beginning of time, but rather a collision between two brains, an event that could repeat, creating a cyclic cosmology where the universe undergoes endless cycles of expansion and contraction. Testing these ideas experimentally is extremely challenging because the extra dimensions and the bulk are not directly observable, but there are indirect ways they might affect our universe. If extra dimensions exist, particles could occasionally escape into the bulk, carrying away energy and momentum, and showing up in experiments as missing energy. Searches at particle colliders have looked for such signals but have found none, placing limits on the size and properties of any extra dimensions. Gravitational waves might carry information about the bulk if their propagation is affected by the higher dimensional geometry, and future gravitational wave detectors with sufficient sensitivity might be able to detect these effects. Despite these possibilities, it remains uncertain whether extra dimensions exist at all, and if they do, whether we will ever be able to detect them. The possibility that entire dimensions of space are hidden from us, that the universe extends into directions we cannot perceive, is a humbling reminder that our three-dimensional experience might be only a slice of a much richer and more complex reality, with most of that reality forever unseen. The philosophical implications. The revelation that we have seen so little of the universe carries profound philosophical implications that challenge our understanding of knowledge, reality, and humanity's place in the cosmos. For centuries, philosophy has grappled with epistemological questions about the limits of human knowledge, asking what we can know, how we can know it, and whether there are things that are fundamentally unknowable. The discoveries of modern cosmology provide concrete examples of these limits, showing that vast domains of reality are inaccessible to observation, not because of temporary technological constraints, but because of the fundamental structure of space-time, causality, and quantum mechanics. This situation calls into question the scientific assumption that the universe is comprehensible, that through observation and reason, we can come to understand how things work. If 95% of the universe is invisible, if most of reality is forever beyond our horizon, if the fundamental structure of space-time is veiled by quantum uncertainty, then how can we claim to understand the cosmos? One response is to adopt a form of humility, acknowledging that our theories are always provisional, always based on incomplete information, and always subject to revision when new observations or new theoretical insights emerge. This humble approach is built into the scientific method, which emphasizes testing hypotheses against evidence and being willing to abandon or modify theories when they fail to match observations. However, it also raises the question of whether there are aspects of reality that we can never test, never observe, and therefore never truly know. The multiverse is a prime example of this problem. If there are other universes beyond our cosmic horizon, causally disconnected from us, then we can never observe them directly. Their existence may be a logical consequence of theories we have good reasons to accept, like inflation or quantum mechanics, but they remain speculative because they cannot be tested. Some philosophers and scientists argue that if a theory predicts unobservable entities, those entities are not part of science, but belong to metaphysics, the branch of philosophy concerned with the nature of reality beyond what can be empirically verified. Others argue that as long as a theory makes testable predictions in the observable domain, its unobservable consequences should be taken seriously, even if they cannot be directly confirmed. This debate has no clear resolution, but it highlights the limits of the scientific method when confronted with aspects of reality that are fundamentally inaccessible. Another philosophical issue is the question of realism, the view that the universe exists independently of our observations, and that scientific theories describe objective features of that reality. The fact that most of the universe is unseen raises questions about the status of our theories. When we describe dark matter and dark energy, are we describing real components of the universe, or are we merely creating mathematical constructs that fit the data without corresponding to anything that actually exists? The history of science includes many examples of theoretical entities that were initially proposed to explain observations, but were later found not to exist. The ether, a hypothetical medium thought to carry light waves, was abandoned after the Michelson-Morley experiment and the development of special relativity. Phlogiston, a substance once believed to be released during combustion, was discarded after the discovery of oxygen and the understanding of oxidation. Could dark matter and dark energy turn out to be similar illusions, artifacts of incorrect theories, rather than real components of the cosmos? Most scientists believe that dark matter and dark energy are real because the evidence for them comes from many independent observations, and because no alternative theory has successfully explained all the data without invoking some form of unseen mass or energy. But the possibility remains that future discoveries could overturn our current understanding, revealing that what we thought was dark matter was actually a modification of gravity, or that what we thought was dark energy was a misinterpretation of cosmic expansion. The philosophical implications extend to questions of meaning and purpose. If the universe is so vast, so old, and so largely hidden from us, what does that say about humanity's significance? Are we just a fleeting, insignificant speck in an incomprehensibly large cosmos? Or does our ability to ask these questions, to explore and understand even a tiny fraction of reality, give us a special status? Different philosophical and religious traditions offer different answers, but the scientific discoveries do not resolve the question. They simply provide the context in which the question must be asked, showing that we are far smaller and the universe far larger than our ancestors imagined, and that most of what exists will remain forever beyond our reach. The humility of science. One of the most important lessons from the revelation of how little we have seen is the need for intellectual humility. Science is often portrayed as a march of progress, a steady accumulation of knowledge that brings us closer to complete understanding. But the discoveries of dark matter, dark energy, and the vast unseen universe remind us that this narrative is too simplistic. Science is not a straight line from ignorance to knowledge, but a winding path with many surprises, setbacks, and revisions along the way. The history of cosmology is filled with examples of confident theories that turned out to be wrong. In the early 20th century, many astronomers believed that the Milky Way was the entire universe, that there were no other galaxies, and that the universe was static and unchanging. Within a few decades, these ideas were overturned by the discoveries of other galaxies, the expansion of the universe, and the Big Bang. In the mid-20th century, the steady-state theory, which proposed that the universe had no beginning and maintained a constant average density through the continuous creation of matter, was widely accepted until the discovery of the cosmic microwave background provided strong evidence for the Big Bang. In the late 20th century, astronomers believed that the expansion of the universe was slowing down until observations of distant supernovae revealed that it was accelerating. Each of these revisions humbled the scientific community, showing that even well-supported theories can be wrong or incomplete. The current standard model of cosmology, often called lambda CDM because it includes a cosmological constant lambda representing dark energy and cold dark matter CDM, fits a wide range of observations, but it leaves many questions unanswered. The nature of dark matter and dark energy, the origin of the matter-antimatter asymmetry, the initial conditions of the Big Bang, the ultimate fate of the universe, all of these are open questions. Future discoveries may confirm the current model in its broad outlines while filling in the details, or they may reveal that the model is fundamentally flawed and needs to be replaced by something entirely different. This uncertainty is not a weakness but a strength of science. It means that science is self-correcting, that it remains open to new evidence and new ideas, and that it does not claim to have final answers. The recognition that we have seen only a tiny fraction of the universe reinforces this humility, reminding us that no matter how much we learn, there will always be more that we do not know, more that we cannot see, and more that we cannot understand. This humility extends to how scientists communicate with the public. Rather than presenting scientific knowledge as absolute truth, scientists must acknowledge the uncertainties, the limitations of the data, and the possibility that current theories may be revised. This honesty is sometimes misunderstood as weakness or indecisiveness, but it is actually a mark of intellectual integrity, a commitment to following the evidence wherever it leads, rather than clinging to preconceived ideas. The revelation of how little we have seen is a powerful reminder that the universe does not owe us understanding, that reality is under no obligation to be simple or comprehensible, and that the pursuit of knowledge is an endless journey rather than a destination to be reached. The role of technology and innovation. Despite the humbling realization of how little we have seen, there is reason for optimism. The history of science shows that technological innovation repeatedly pushes the boundaries of observation, revealing previously hidden aspects of reality. The invention of the telescope in the early 17th century transformed astronomy, allowing Galileo to discover moons orbiting Jupiter, phases of Venus, and countless stars invisible to the naked eye. The development of spectroscopy in the 19th century allowed astronomers to determine the chemical compositions of stars and to measure their motions through the Doppler shift. The invention of radio telescopes in the mid-20th century revealed a universe of pulsars, quasars, and other phenomena invisible at optical wavelengths. Each technological advance has opened new windows on the cosmos, and there is no reason to think that this process has reached its end. Current and future technologies promise to reveal more of the universe than ever before. Gravitational wave detectors, both ground-based and space-based, will detect signals from a growing range of sources, mapping the population of black holes and neutron stars, and potentially detecting gravitational waves from the Big Bang itself. Neutrino observatories, expanding in size and sensitivity, will capture more signals from supernovae, active galactic nuclei, and other energetic sources, building a neutrino map of the universe. Next-generation telescopes, like the extremely large telescope with its 40-meter mirror and the James Webb Space Telescope with its sensitivity to infrared light, will see farther and more clearly than any previous instruments, detecting the faint light from the first galaxies and studying the atmospheres of exoplanets in search of signs of life. Direct dark matter detection experiments, using ever larger and more sensitive detectors, may finally capture the elusive particles that make up dark matter, revealing its nature and properties. Particle accelerators, if scaled up to higher energies, might create dark matter particles in collisions, allowing their properties to be studied in the laboratory. Computer simulations running on supercomputers capable of trillions of calculations per second will model the universe in ever greater detail, testing theories against observations and predicting phenomena that can be searched for. Artificial intelligence and machine learning are also playing increasing roles in astronomy, analyzing vast data sets to find patterns that would be impossible for humans to detect manually. Machine learning algorithms can identify distant galaxies in telescope images, classify transient events like supernovae, and even predict the properties of unseen objects based on statistical correlations in the data. These tools are accelerating the pace of discovery and allowing scientists to extract more information from observations than was possible with traditional methods. Beyond technology, theoretical innovation is also essential. New mathematical frameworks, new physical insights, and new ways of thinking about the universe can reveal hidden connections and suggest new observations to make. The history of physics is filled with examples where theoretical breakthroughs preceded experimental confirmation, as when Einstein predicted gravitational waves decades before they were detected, or when Dirac predicted the existence of antimatter based on the mathematical structure of quantum mechanics before the positron was discovered. Future theoretical advances may similarly point the way to understanding dark matter, dark energy, and other mysteries of the unseen universe. The combination of technological and theoretical innovation offers hope that the fraction of the universe we can observe and understand will continue to grow, even if it never approaches 100%. Each new discovery reveals new questions, ensuring that the frontier of knowledge always extends beyond what has been explored. But the process of exploration itself is one of humanity's greatest achievements, a testament to curiosity, ingenuity, and the refusal to accept ignorance as a permanent state. The interconnection of science. The revelation of how little we have seen highlights the interconnected nature of scientific knowledge. Understanding the universe requires insights from many different fields, from particle physics to cosmology to astronomy to computer science, and advances in one field often depend on progress in others. The study of dark matter, for example, involves particle physicists who propose candidate particles and design experiments to detect them, astronomers who map the distribution of dark matter through gravitational lensing and galaxy dynamics, and cosmologists who study how dark matter affects the evolution of cosmic structure. Solving the dark matter mystery will require collaboration across these disciplines, sharing data and insights, and developing theories that are consistent with observations from all domains. Similarly, understanding dark energy requires knowledge of general relativity, quantum field theory, and observational cosmology, integrating theoretical predictions with measurements of supernovae, the cosmic microwave background, and the large-scale structure of galaxies. The search for gravitational waves brought together physicists who designed the detectors, engineers who built the precision instruments, and astronomers who studied the sources and interpreted the signals. The study of exoplanets involves planetary scientists who understand how planets form, astronomers who detect and characterize these distant worlds, and astrobiologists who consider the conditions necessary for life. This interconnection means that progress in one area can lead to breakthroughs in others, as new techniques, new data, or new theoretical ideas across disciplinary boundaries. It also means that the revelation of how little we have seen is a shared realization across all of science, a recognition that no single field has a complete picture, and that understanding the universe requires integrating knowledge from many sources. Educational systems that encourage interdisciplinary thinking, that train students to work across traditional boundaries, and that foster collaboration between different fields are essential for making progress on the big questions that remain unanswered. The challenges of studying the unseen universe are too large for any single discipline or any single nation to tackle alone, and the solutions will emerge from global collaborations involving thousands of scientists working together toward common goals. This interconnected nature of science also means that discoveries in seemingly unrelated fields can have unexpected impacts. The development of quantum mechanics in the early 20th century, motivated by the desire to understand atomic spectra and the behavior of electrons, has led to technologies like transistors, lasers, and magnetic resonance imaging that have transformed society. The study of general relativity, initially a purely theoretical exploration of gravity and spacetime, has practical applications in GPS systems, which must account for relativistic effects to provide accurate positions. Similarly, the current quest to understand dark matter and dark energy, driven by curiosity about the cosmos, may lead to unexpected technological spin-offs, new materials, new detection methods, or new computational techniques that have applications far beyond astronomy. The interconnection of science ensures that even the most abstract and seemingly impractical research can have profound and unforeseen impacts, justifying the investment of resources in exploring the unknown. The narrative of exploration. Throughout human history, exploration has been central to our identity as a species. From the first humans who left Africa and spread across the globe, to the navigators who crossed oceans to discover new continents, to the astronauts who traveled to the moon, exploration has driven innovation, shaped cultures, and expanded our understanding of the world. The exploration of the universe is the latest chapter in this grand narrative, a continuation of the same impulse that led our ancestors to wonder what lay beyond the next hill or across the sea. The revelation that we have seen so little of the universe does not diminish the value of exploration. If anything, it makes the endeavor more meaningful, showing that there is an almost unlimited frontier still to be explored, that the journey of discovery is far from over, and that future generations will have opportunities to make their own contributions. The fact that 95% of the universe is unseen means that there is 95% still waiting to be discovered, 95% of mysteries still to be solved, 95% of reality still to be understood. This vast unseen universe is not a barrier but an invitation, a call to keep pushing the boundaries, to keep asking questions, and to keep seeking answers. The narrative of exploration is also a narrative of human achievement. Every discovery, from the heliocentric model of the solar system to the detection of gravitational waves, represents the culmination of effort by countless individuals, each contributing a small piece to the larger picture. The scientists who propose theories, the engineers who build instruments, the technicians who maintain them, the students who analyze data, the educators who train the next generation, all are part of this collective endeavor. The revelation of how little we have seen is a testament to the progress that has been made, showing that we have come far enough to recognize the limits of our knowledge, to understand that most of the universe is hidden, and to begin developing the tools and theories needed to explore it. This progress is something to be celebrated, even as we acknowledge how much remains unknown. The narrative of exploration also includes the stories of individuals, the scientists whose curiosity and determination drove breakthroughs. Fritz Zwicky, who first proposed the existence of dark matter, faced skepticism and ridicule, but persisted because he believed the evidence. Vera Rubin, whose observations of galaxy rotation curves provided compelling evidence for dark matter, had to overcome barriers faced by women in science in the mid-20th century. Saul Perlmutter, Adam Rees, and Brian Schmidt, who led the teams that discovered the accelerating expansion of the universe, spent years carefully measuring distant supernovae and checking their results before announcing a discovery that seemed impossible. These stories remind us that science is a human endeavor, carried out by people with passion, creativity, and perseverance, and that the exploration of the unseen universe depends on the contributions of individuals who are willing to challenge assumptions and pursue difficult questions. The vision of the future. Looking ahead, the future of studying the unseen universe is filled with promise and challenge. In the coming decades, new observatories and experiments will come online, providing unprecedented views of the cosmos and potentially answering some of the biggest questions in science. LISA, the space-based gravitational wave detector, scheduled for launch in the 2030s, will observe supermassive black hole mergers and other low-frequency sources, revealing a population of gravitational wave events that is completely invisible to ground-based detectors. The Square Kilometre Array, a radio telescope under construction in Australia and South Africa, will be 50 times more sensitive than any existing radio telescope, allowing it to map the distribution of neutral hydrogen throughout the universe and to study the formation of the first stars and galaxies. The Vera Rubin Observatory, previously known as the Large Synoptic Survey Telescope, will begin operations in the mid-2020s and will survey the entire southern sky every few nights, creating a movie of the universe that will reveal transient events like supernovae, asteroids, and variable stars. The Dark Energy Spectroscopic Instrument, or DESI, is currently conducting a 5-year survey to measure the redshifts of tens of millions of galaxies, mapping the large-scale structure of the universe in unprecedented detail and testing theories of dark energy. The Euclid space mission, launched in 2023, will map the distribution of galaxies and dark matter across a large fraction of the sky, using gravitational lensing to study how structure has evolved over cosmic history. These projects, along with many others, will generate vast amounts of data, far more than can be analyzed by traditional methods, necessitating the development of new data analysis techniques, increased use of machine learning, and greater collaboration between astronomers worldwide. The data will be made publicly available, allowing scientists and even amateur astronomers to explore the observations and make their own discoveries. In the longer term, even more ambitious projects are being planned or proposed. A space telescope larger than Webb, with a mirror tens of meters across, could directly image Earth-like planets around nearby stars and search for signs of life in their atmospheres. A particle collider larger than the Large Hadron Collider, perhaps 100 kilometers in circumference, could reach higher energies and potentially create dark matter particles, or discover new forces and particles predicted by theories beyond the standard model. A gravitational wave detector on the Moon, using the Moon's surface as a sensor, could detect ultra-low frequency waves from the early universe. A neutrino detector even larger than Ice Cube, perhaps using the entire Pacific Ocean or a large salt mine, could capture more neutrinos from astrophysical sources and study the neutrino universe in greater detail. These are long-term visions, requiring decades to realize, and enormous investments of resources, but they represent the scale of ambition needed to explore the 95% of the universe that remains unseen. Whether all of these projects will be built depends on many factors, including funding, political support, technological feasibility, and the priorities of the scientific community and society as a whole. But the fact that such projects are being seriously discussed shows that the exploration of the unseen universe is not just a theoretical exercise, but a practical endeavor that is actively being pursued. The cosmic connection. One of the most profound insights from studying the universe is the realization that we are made of the same stuff as stars, that the atoms in our bodies were forged in the nuclear furnaces of stars that died billions of years ago, and that we are connected to the cosmos in a direct, physical way. This connection, articulated beautifully by Carl Sagan in the phrase, "We are made of star stuff," is not just poetic, but literal. The hydrogen in water, the calcium in bones, the iron in blood, all were created in stars or in the Big Bang, and they have cycled through the cosmos for billions of years before becoming part of us. The revelation that we have seen so little of the universe adds another dimension to this connection. If 95% of the universe is invisible, then most of the matter and energy that influence the formation of stars, galaxies, and planets, and ultimately the conditions that allowed life to arise on Earth, is made of things we have never seen and cannot directly detect. We are not just made of star stuff, but are also shaped by dark matter and dark energy, by invisible components that govern the gravitational collapse of gas clouds into stars, the formation of galaxies, and the large-scale structure of the cosmos. Without dark matter, galaxies would not have formed, or would have formed much later, and without galaxies, there would be no stars, no planets, and no life. In this sense, we owe our existence to the unseen universe, to the dark matter halos that provided the gravitational scaffolding for structure formation, and to the dark energy that determines the expansion rate and the ultimate fate of the cosmos. This connection is humbling and awe-inspiring, showing that we are intimately tied to aspects of reality that we do not understand, that our very existence depends on phenomena that remain deeply mysterious, and that the story of how we came to be is incomplete without understanding the unseen 95%. The cosmic connection also extends to the future. The fate of the universe, driven by dark energy, will determine the fate of all matter, including any life that arises in the future. If dark energy continues to accelerate the expansion, then in the distant future, galaxies outside our local group will recede beyond the cosmic horizon, becoming forever inaccessible. Stars will exhaust their fuel and die, leaving only cold remnants, and eventually even these will decay or evaporate, leading to a cold, dark, empty universe where no structures remain. Alternatively, if dark energy behaves differently than we think, the universe might collapse in a big crunch, or it might be ripped apart in a big rip if dark energy grows stronger over time. Understanding the unseen universe is thus not just an intellectual exercise, but a quest to understand our origins, our place in the cosmos, and the future of everything. The connection between ourselves and the universe, between the seen and the unseen, between the known and the unknown, is the thread that ties together all of cosmology and all of our efforts to understand reality. The emotional weight of discovery. Beyond the scientific facts and philosophical implications, the revelation of how little we have seen carries an emotional weight that affects how we see ourselves and our place in existence. There is a sense of smallness, of insignificance, that comes from realizing that everything we have ever known is confined to a tiny, tiny fraction of reality. The Earth, our home, is a speck in the solar system. The solar system is a speck in the Milky Way galaxy. The Milky Way is one of trillions of galaxies, and all of those galaxies, all of that visible matter, represents less than 5% of what exists. This perspective can be overwhelming, even frightening, forcing us to confront the vastness of a universe that does not care about us, that existed for billions of years before we appeared, and will continue for billions or trillions of years after we are gone. Yet there is also wonder and beauty in this revelation. The fact that we, as conscious beings, can ask these questions, can build instruments to probe the cosmos, can develop theories to explain what we observe, is extraordinary. We are the universe becoming aware of itself, a tiny part of the cosmos that has gained the ability to reflect on the whole. The fact that we have seen so little makes the journey of discovery more meaningful, not less. Every observation that reveals something new, every theory that explains a previously mysterious phenomenon, every experiment that pushes the boundaries of knowledge is a triumph of human curiosity and ingenuity. The emotional response to the unseen universe is also shaped by our individual perspectives and values. For some, the mystery is exciting, a challenge to be embraced, an opportunity to explore and discover. For others, it is humbling, a reminder of the limits of human understanding and the need for intellectual modesty. For still others, it is frightening, a confrontation with the unknown that highlights our vulnerability and insignificance. There is no right or wrong emotional response, and different people will feel different things when confronted with the vastness of the unseen universe. What is important is to allow ourselves to feel these emotions, to sit with the wonder and the fear, the curiosity and the humility, and to let them inform how we approach the world. The study of the universe is not just a rational enterprise, but also an emotional and even spiritual one, engaging the whole person, mind and heart, in the quest to understand reality. The revelation of how little we have seen is an invitation to be amazed, to be humbled, and to be inspired, to recognize that we are part of something far greater than ourselves, and to find meaning and purpose in the act of exploration itself, regardless of whether we ever fully understand the cosmos. The legacy we leave. As we contemplate the unseen universe and the limits of human knowledge, it is worth considering what legacy we will leave for future generations. The scientific knowledge we accumulate, the instruments we build, the theories we develop, and the data we collect will all be passed down to those who come after us, providing the foundation for future discoveries. But beyond the tangible products of science, we also leave a legacy of curiosity, of the willingness to ask difficult questions, of the courage to confront the unknown, and of the commitment to seeking truth through evidence and reason. This legacy is perhaps more important than any individual discovery, because it represents a way of thinking, a set of values that transcend specific facts or theories. The revelation that we have seen so little of the universe is itself part of this legacy. By acknowledging the limits of our knowledge, by being honest about what we do not understand, we set an example of intellectual humility that future generations can follow. We show that science is not about having all the answers, but about asking the right questions, about being open to new evidence, and about being willing to revise our understanding when necessary. This attitude is essential for progress because it prevents dogmatism, the hardening of ideas into unquestionable truths, and it keeps the door open for new insights and new discoveries. The legacy we leave also includes the instruments and infrastructure of science. The telescopes, detectors, and observatories we build today will continue to be used by future scientists, and the data we collect will be analyzed and reanalyzed for years to come, often revealing things that the original observers did not notice. The Hubble Space Telescope, for example, has been in operation for more than 3 decades, and its archive contains observations that are still being studied, with new discoveries being made from data that was collected years ago. The same will be true of Webb, LIGO, and other major instruments. The investment in these tools is an investment in the future, providing resources that will benefit generations to come. Beyond science, the legacy we leave includes the cultural and societal attitudes toward exploration and knowledge. If we foster a culture that values curiosity, that supports education, and that invests in research, then future generations will be better equipped to continue the exploration of the unseen universe. If we fail to do so, if we become complacent, or if we prioritize short-term gains over long-term understanding, then the progress may slow or even stop. The choices we make today, as individuals and as a society, will shape the future of science and the future of humanity's relationship with the cosmos. The revelation of how little we have seen is a call to action, a reminder that there is so much more to learn, so much more to discover, and that it is our responsibility to continue the journey and to pass the torch to those who will follow. The infinite horizon. And so we arrive at the end of this exploration, this journey through the humbling revelation that scientists have just shown us how little of the universe we have truly seen. We have traveled from the discovery of dark matter and dark energy to the realization that ordinary matter makes up less than 5% of the cosmos, from the cosmic horizon that limits what we can observe to the quantum veil that hides the smallest scales, from the missing baryons to the unseen neutrinos, from the gravitational wave universe to the possibility of extra dimensions, and through all the ways in which reality remains largely hidden from our instruments and our understanding. The central truth we have confronted tonight is one of profound humility. Everything we have ever studied, every galaxy photographed, every star catalogued, every particle detected, represents less than 5% of what exists. The other 95% is invisible, unreachable, and deeply mysterious, composed of dark matter that we cannot see and dark energy that defies explanation. Even within the small fraction that is ordinary matter, we have observed only a tiny portion, with most stars never individually catalogued, most planets never detected, and vast regions of space never explored. This revelation is not a cause for despair but for wonder. It shows that the universe is far richer, far more complex, and far more mysterious than we ever imagined. It means that the frontier of discovery stretches endlessly before us, that there are countless mysteries still to be solved, and that future generations will have opportunities to make their own contributions to the grand narrative of exploration. The fact that we have seen so little does not diminish what we have achieved. On the contrary, it highlights the remarkable progress of science, showing that we have come far enough to recognize the limits of our knowledge, to understand that most of the universe is hidden, and to begin developing the tools and theories needed to explore it. This progress is a testament to human curiosity, ingenuity, and perseverance, to the willingness to ask difficult questions and to pursue them even when the answers seem impossibly distant. As you settle into rest now, as your breathing slows and your body relaxes, let these thoughts drift through your mind, like clouds across an endless sky. Imagine the vast unseen universe stretching beyond the reach of our telescopes, filled with dark matter halos, threaded with invisible gravitational waves, permeated by neutrinos and cosmic rays, structured by forces we do not yet understand. Imagine the galaxies we will never see, beyond the cosmic horizon, forever moving away from us as space expands. Imagine the tiny quantum realm beneath the Planck scale, where space-time itself becomes uncertain and reality takes on forms we cannot visualize. Imagine the hidden dimensions that might exist at every point in space, curled up so tightly that we cannot perceive them. All of this is out there, or in here, woven into the fabric of existence, shaping everything we see, even though it remains invisible. The revelation that we have seen so little is an invitation to remain curious, to stay humble, and to continue the journey of exploration. It is a reminder that the universe does not owe us understanding, that reality is under no obligation to reveal itself, and yet we persist in seeking knowledge because that is what it means to be human. We look up at the stars, we build our instruments, we ask our questions, and slowly, patiently, we peel back the layers of mystery, one discovery at a time. most of the universe will remain forever unseen, hidden behind horizons we cannot cross, veiled by limits we cannot transcend. But the small fraction we can observe and understand is enough to fill us with awe, to inspire generations of scientists, and to show us that we are part of something far greater than ourselves. The cosmos is vast and ancient and filled with wonders beyond counting, and we are privileged to live in a time when we can explore it, when we can push the boundaries of the known and venture into the unknown, when we can look out into the darkness and find light, find structure, find meaning in the patterns that emerge from the chaos. Sleep well, explorer, knowing that the universe is far larger than what you can see, that most of reality remains hidden, and that this is not a limitation but an opportunity, not an end but a beginning. The journey to understand the cosmos is far from over. In fact, we have only just begun, and the revelation of how little we have seen is the first step in a much longer voyage. A voyage that will continue as long as there are curious minds willing to look up and ask, what else is out there that we have not yet seen?